Today we're going to talk about the electromagnetic spectrum. This is where Einstein dominated. This is where when we talk about light. What does light look like? How does it behave? Things like that. Well, to go into how it behaves, before the 1900s, scientists thought that light behaved solely as a wave. So you could describe the behavior of light by describing the behavior of a wave. But then about 1905, Einstein came along and Planck and a couple of other people, and they changed that belief. They said now that light doesn't only behave like a wave, but sometimes it behaves like a particle, similar to what we saw with Schrodinger. And we had that there was a duality. So light can behave like a wave, and sometimes it can behave like a particle. So we're going to focus today on the wave aspect of the light, and then next class period we'll focus on the particle aspect of the light. So many of light's properties can be described in terms of a wave. The mathematical equations we use can be described in terms of a wave. And light, as it travels through space, behaves like a wave. And we call that electromagnetic radiation. It's a form of energy. Okay, so what is the electromagnetic spectrum? The electromagnetic spectrum is the complete spectrum or the continuum of all forms of light. So what does that mean? So if we're talking about the electromagnetic spectrum, we're talking about different portions of light all put together. So that's going to include your visible light, your ultraviolet, your X-ray, your microwave, things like that. It's the entire spectrum of all different types of electromagnetic radiation. Because your electromagnetic wave consists of electric and magnetic fields that vibrate, that makes your waves. And that's why we describe light in terms of waves. So there are many things that electromagnetic spectrum consists of. Again, it consists of all the different types of light, all the different types of radiation, the entire spectrum. And those include radio waves, cell phone waves, which a lot of times are included in with those radio waves, your microwaves, your radar waves, your infrared, your visible, your ultraviolet, your gamma, and your X-rays. If you look to the right, you'll see two different ways of demonstrating the whole spectrum that is made up of all the different types of radiation. So if you look at the slide, if you look at the electromagnetic spectrum on the top here, if you look here, this portion right here, you'll see that this is your wavelength. So it's showing, going across, your wavelength is decreasing. It's becoming smaller. So things with the largest wavelengths are on the left. The things with the largest wavelengths, smallest wavelengths are on the right. Okay. It's also displayed in terms of frequency. Increasing frequency. A thing with the least frequency is on the left. The thing with the most frequency is on highest frequency is on the right. So in this top one, we have radio waves have the lowest frequency, highest wavelength, and gamma rays are on the right. On the bottom, you have it displayed in the opposite direction. Instead of being decreasing wavelength, the bottom right, it is shown as increasing wavelength. So instead, we have gamma on the left and radio on the right. It's important that you recognize how your spectrum is being displayed. You need to know your units. Here's yet another couple ways of displaying it. We're going to talk about the image on the left. The one on the right is just more so you can see what these different things are used for. But if we're talking about radio waves, if you look at the radio wave, it is a what we call a long wavelength. It's got a long wavelength. It is very broad. Each wavelength of a radio wave is about the size of a building or larger. When we're talking about a microwave, your wavelengths are getting a little bit shorter, and they're about the size of a human instead of the size of a building. So they've gotten a little smaller. Your infrared waves are about the size of a honeybee. Your visible is about the size of a pinpoint. Your ultraviolet is kind of in between a protozoa and molecules. Your X-rays, this is why they're so powerful, they penetrate down to the molecule level. And your gamma rays are looking at your wavelengths are looking at the size of an atom or atomic nuclei. So they're very, very small. The broader your wavelength or the longer your wavelength, the smaller your frequency because you see less of them. As opposed to over here in the gamma rays, they are very, very sharp. So you're going to see more of them. So your properties of your electromagnetic waves can include speed, frequency, and wavelength. Speed would denote with a C because it's a very specific speed. It is the speed of light. All light travels at the speed of light, which we call C, and that's about 3.00 times 10 to the 8 meters per second in a vacuum. And it's going to go slightly slower if it's light going through matter. In this class, we will assume that it's always going at the speed of light. Okay. We have frequency, and frequency can be denoted with an F or this little like V-looking thing. That's called a nu. Those are the two symbols you see for frequency. And it can be denoted by wavelength. Wavelength is a lambda. So these waves can be described by this equation. The speed of light is equal to frequency times wavelength. Speed of light is equal to frequency times wavelength. Because the speed of light is a constant, it does not change. The product of frequency and wavelength must always equal that constant. That means if your frequency is going to go up, then your wavelength has to go down. They are an indirect relationship. It is an inverse relationship. As your wavelength increases, your frequency by default has to decrease. As your wavelength decreases, your frequency must increase. They have an inverse relationship, and we'll talk about that a little bit more in a minute. Okay, but let's define what a wavelength is. So first of all, we denote wavelength with the symbol lambda. This Greek symbol, okay, lambda. And a wavelength is the distance between equal points on a curve. For example, the distance between crest, which is the top of your wavelength, crest to crest, or between your trough to trough, that's the bottom part of your wavelength. That's the bottom part of your wave. That is a wavelength, but it's from distances at equal points of the curve. So if you look at this over here on the right, if you select this point here to start, then you can go to that equal point on the next part of the curve. That's also a wavelength. And because it's a distance, it's usually given in meters or nanometers. You must know the unit you're given because you must be able to convert back to meters. So if it's given to you in nanometers, you must be able to convert it to meters. But we know how to do that because we know our metric prefix. Okay, next we have frequency, and that's denoted with an F or that little nu. And that's the number of waves that pass a given point in a specific time, usually 1 second. So that means if you're standing and staring at one point, at one location for 1 second, how many waves go past you? That's your frequency. So if you have a wave that's very long or broad, in 1 second, you're probably not going to see much of that wave, or you're not going to see many waves. As opposed to if you have a wave that's very, very narrow, then you're probably going to see many waves during that 1 second. That is frequency. And that's measured in waves per second. A lot of times it's denoted as an S to the -1. It's also denoted as a 1 over S, and that is equal to a hertz. So anytime you see hertz, Hz, you should automatically change the unit to S to the -1 or 1 over S. So what does that look like? So for instance, if you have 300 hertz, that's the same thing as 300 1 over a second. That's your unit. Or 300 seconds to the -1. It's your unit. These are all equivalent. Okay. So as we said earlier, your wavelength and your frequency have an indirect or an inverse relationship. As one increases, the other decreases. So for instance, if this is a time period you're looking at, let's say it's 1 second, that distance right there. These are both 1 second. If you have a short wavelength, that means a wavelength that is pretty narrow, you're going to see a lot of more waves going past you in that 1 second than if you have a long wavelength. So if you have a short wavelength, you have high frequency. If you have a long wavelength, you have low frequency. Okay, the next thing we need to define is amplitude. Amplitude is the wave's height from origin to crest. Okay, so this is a wave. If we bisect that wave in two, cut it in two, you draw that line. That guy is called your origin. That line that bisects your wave is called your origin. Your amplitude is the wave's height from the origin to the crest. The crest is the very, very top of your wave. That's your crest. So your amplitude is going to be from the origin to the crest. Or it could be from the origin to the trough. The origin to the trough. That is your amplitude. So on a wave, you need to be able to label 5 things. You need to be able to label a wavelength. You need to be able to label the origin, your crest, your trough, and your amplitude. Let's do that again. Wavelength, origin, crest, trough, and amplitude. Those are things you will need to be able to label on your wave. So to remind you, electromagnetic spectrum is that continuum of all the different forms of electromagnetic radiation. Your electromagnetic spectrum shows you all forms of electromagnetic radiation. So what is electromagnetic radiation? Well, electromagnetic radiation, one form of electromagnetic radiation would be your radio waves. Another one would be your X-rays. Another one would be your gamma rays. Another one would be infrared. All of those put together, plus the ones I haven't mentioned, are part of your electromagnetic spectrum. So we're going to go through each one of these types of electromagnetic spectrum one at a time. And we'll start with the lowest energy ones, the radio waves, or the broadest wavelength, the radio waves, and end with the highest energy, highest energy, shortest wavelength, which is gamma. Okay, so let's start with radio waves. Radio waves are low energy waves that have long wavelengths. They include FM, AM, radar, TV waves. They also include your cell phone waves. They have wavelengths of 10 to the negative 1, so 0.1 meters and longer, in other words, larger than 1.1 meter. They're low frequency. Low frequency. Long wavelength, low frequency. Low energy. These are not very energetic. They're not very dangerous. They're used in many devices. They're used in remote control items. This is how you use your, like when people talk on CB radios, they're using your radio waves. They're used in cell phones. They're used in wireless devices, things like that. Remember, these are very broad. Okay, next we have microwaves. If you ever see a tower that looks like this, like little drums attached to a tower, those are microwaves. Okay, they're shorter wavelengths than radio, so they're getting a little more narrow, but they're longer than infrared and visible, which comes next. They have lower energy than infrared and visible, but they're higher energy than radio. So our wavelength got smaller, but our energy and our frequency has increased. The wavelengths that are important are 1 times 10 to the minus 4 meters to 1 times 10 to the minus 1 meters. So that's 0.1 meters to 0.0001 meters. They're used in communication, they're used in medicine, and they're used to cook your food. The way your food gets cooked in a microwave is that you put this wave on your food, and the water molecules in your food respond to that microwave radiation, and they start to vibrate. And just like you, when you vibrate and move around and bounce around, you start getting a little warm. So do these water molecules. And that is why that's why microwaves work. You're using the fact that your food has water in it. Okay. Next, we have infrared. This is invisible electromagnetic waves that are detected as heat. You can't see it, but you can feel it. Okay, these infrared waves are detected as heat. They can be detected using night goggles because you're just seeing the differential in heat. They're used in your heat lamps. They're used in TV remote control devices. They have more energy and higher frequency than microwaves, but lower than visible. And their wavelengths have gotten a little even more narrow. So we went from radio, which were very broad wavelengths, to microwaves, which were a little more narrow. And now infrared is a little more narrow than that as well. Okay? Which then leads us to visible light. This is the only light that we actually can see with our eyes. We can detect infrared via heat, but the only thing we can see with our eyes is visible light. And this is that Roy G. Biv you learned about in elementary school. The color, the rainbow, red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. Portion of the electromagnetic spectrum that the human eyes can detect. Okay, and this is important to know. Your wavelengths range from 700 nanometers, that's where your red light is, to 400 nanometers, and that's where your violet light is. And the rest is in between. The red light has lower frequency but broader wavelengths. The violet light has higher frequency but shorter wavelengths. And this is what your spectrum looks like. If you look here, this is where your red is at 700 nanometers. This is where your purple is at 400 nanometers. Now, if you look, the red part of your light borders your infrared, and the violet part of your light borders your ultraviolet. Infrared is by red, ultraviolet is by violet. Your red has the lowest frequency, but the largest wavelength. Your violet has the shortest wavelength, but the highest frequency, highest energy out of the visible light. Okay, let's talk about ultraviolet. Again, the ultraviolet borders the violet portion of the visible spectrum. It is higher energy, higher frequency than visible light waves, and they range from 400 nanometers to 10 nanometers. So their frequency and therefore their energy is high enough to penetrate living cells and can cause them damage. This is why you need to wear sunblock, because it's penetrating living cells. It can cause if you get ultraviolet waves, ultraviolet radiation hitting your skin, it can cause skin cancer. It also causes blindness in humans. This is why we should wear sunglasses when we're outside. Our ozone layer absorbs ultraviolet radiation very, very well, which protects us from those rays coming to the part of the earth that we live on, the troposphere. Okay, but if that ozone layer isn't there, then we're going to have these high energy waves that are going to cause skin cancer. They're also used in tanning beds and sterilizing equipment. So when you go to a tanning bed and you get tan in 15 minutes, the reason is because you are penetrating your living cells with these ultraviolet waves. They're not good for you. It's also used in sterilizing equipment. We can't see it with the eye, but bees and bats and butterflies and small rodents can all see it. Okay, next we have X-rays. These are high energy waves. They range from 10 nanometers to 0.001 nanometers. And these can have enough energy to penetrate deep into tissues, not your cells on your skin, deep into tissues, and can cause damage to cells. So this is the reason why if you are pregnant, you will never get an X-ray, because your X-rays can cause damage to cells. And when you are pregnant, cells are developing, and you don't want to cause that damage to those developing cells. They can be stopped by dense materials such as bone. So when you get an X-ray, your X-ray is penetrating through everything else except for the bones, which is why you see that outline of the bones. X-rays, again, you want to minimize how much you use of it because they can also cause cancer. So anytime you get an X-ray, you protect any part of your body that is not being X-rayed, just to minimize that radiation you're getting. And it's used in medicine, it's used in industry, and it's used in astronomy. Okay, now we got to go to the big daddy of them all. That is gamma rays. That's the highest form of energy. It comes out of the big nuclear reactor in the sky, our sun. And our Earth's atmosphere does a really, really good job of protecting us at the surface from your gamma rays. They're very, very highly energetic. When they talk about astronauts being exposed to radiation, this is what they're worried about. They're worried about these gamma rays because they're out in space. They don't have an Earth's atmosphere to protect them from this radiation. Gamma rays are strong enough that have enough energy that can go through materials very easily. They're very, very narrow, very highly energetic, narrow wavelengths. You would need 3 to 4 feet of thick concrete wall to even stop it at all. Gamma rays, though, you can find them on here on Earth. You can find them in nuclear reactions. In nuclear power plants, you can find them in nuclear bombs. And because they're so high energetically, those nuclear bombs have long-lasting effects generations to come because you are changing things down to the atomic range. They're also caused by naturally occurring elements on Earth. What does that mean? All those radioactive elements we have on Earth, to the bottom of your periodic table, those at the bottom we've got the F block. Those are your radioactive elements. So there is gamma rays that are produced by your naturally occurring elements, but we try to protect ourselves from it. And when we get to the radiochem, the nuclear chemistry section of this class, we'll talk about it a little bit more. Gamma rays is also what's used in treatment of cancer. So when we hear about somebody getting radiation for their cancer, this is what they're getting. So to remind you, what we said at the beginning was your electromagnetic waves can be described by a mathematical relationship. We said that the speed of light, c, which is 3.0 times 10 to the 8 meters per second, is equal to the wavelength, lambda, in meters, times our frequency in hertz, or per second, or 1 over a second. So we're going to be calculating what is the frequency given a certain wavelength. What is the wavelength given a certain frequency? C, our speed of light will never change. We're only changing frequency or wavelength. So this is the equation you're using. So let's practice. So here we've got a question. It says, violet light has a wavelength of 4.10 times 10 to the minus 12 meters. What is its frequency? So first let's write down what's given to us and what we want. So we want frequency, and we want that in per seconds per hertz. Excuse me. What is given to us? Wavelength, 4.10 times 10 to the minus 12 meters. Let's write our units down always. What else do we know? Well, we know the speed of light, 3.0 times 10 to the 8 meters per second. And this is the equation we're going to use. If you look, we know C, we have a value for C. We have a value for wavelength. So we're just going to solve for frequency. So doing some algebra, or you can use your triangle, which I will discuss in class. You can rearrange this equation to solve for frequency. How do we rearrange it? Well, we divide both sides by lambda. Lambdas cancel out on this side. You're left with c over lambda on the other side. So now it's just a matter of entering things into your calculator. C is 3.0 times 10 to the 8 meters per second. Lambda is 4.10 times 10 to the minus 12 meters. If you notice, your meters are going to cancel out. What unit are we going to be left with? 1 over a second. 1 over a second, which is what we want, which is a hertz, because we're trying to find frequency. Make sure when you enter this into your calculator that you don't forget to enter your exponents. And I would pause right now the video to make sure you can enter this into your calculator properly. Remember, 1 over a second is the same thing as a hertz. In the last problem, we solved for frequency. Now we're going to solve for wavelength. This problem says, what is the wavelength of light? So we're trying to find wavelength with a frequency of 7.66 times 10 to the 14 hertz. Anytime you see hertz, change it into its units, 1 over seconds. So what is given to us? Our frequency is given to us. We're trying to find wavelength, and we know C. Okay? Using that equation, and using the equation that we had before, we can rearrange the equation, and you get lambda is equal to C over F. Now it's just a matter of entering things into your calculator. Remember, when you have hertz, automatically change it into its unit. So if I've done that here, hertz, this number here is 1 over second. So if you enter this into your calculator, if you notice, your 1 over second cancels out with the 1 over seconds here. And you're left with a unit of meters, which is what you want for wavelength. You enter this into your calculator, you get 3 significant figures. Your answer should be 3.92 times 10 to the minus 7 meters. Or you could say this is 392 nanometers. Okay, so why don't you try this problem and pause the video and try this problem. Okay, so what you should have done is you have C over lambda over F, rearrange that equation. Now it's a matter of just entering our numbers into our calculator. Should have been 3 significant figures, so this is actually incorrect. I think it's 0.0897, I don't remember offhand, but this should be 3 significant figures because this is 3 significant figures. And this should be 3.00 times 10 to the 8 because we know the speed of light pretty well. Okay, let's try another one. Pause the video and see if you can do this one. We're trying to find the frequency of green light that has this wavelength, 490 nanometers, or 4.90 times 10 to the minus 7. So please pause the video and try to solve this problem. Okay, again, same equation, but now we're solving for frequency. We rearrange our equation. We put speed of light on the top. That should say 3.00 times 10 to the 8 meters per second. That's a little lazy there. Divided by 4.90 times 10 to the minus 7 meters. Our meters cancel out. We're left with 1 over a second, which is what we want for frequency. We enter into our calculator and we get 6.12 times 10 to the 14, 1 over second, which is the same as a hertz. 3 significant figures. Okay, we'll do a couple more practice problems. So you'll practice a couple more and I will share the answers with you and then we will discuss one problem at the very end. So here you're calculating the frequency of light emitted in a mercury lamp with this wavelength. Okay, this is 436 nanometers. This is actually in the visible range, close to the infrared. So I will pause the video. I would pause the video if I were you, try to solve the problem, and I will display the answers in a second. Okay, we're using the same equation. We know our C. We're trying to solve for F. We'll multiply it times our wavelength. So here I just haven't rearranged it yet. I will rearrange it here. Divide both sides by 4.36 times 10 to the minus 7. And I get this number to 3 significant figures. 3 significant figures. Okay, another practice problem. Calculate the frequency of light emitted by a mercury lamp. It's the same problem here, it's just showing you how to rearrange the equation. I don't know why that's there twice. Okay, so last but not least, one thing I want you to remember is 1 meter is equal to 1 times 10 to the 9 nanometer. So if you have 450 nanometers, that's the same thing as 450 times 10 to the minus 9 meters. You need to be able to go between your metric prefixes because you might have a situation where that is important. So for instance, here, it says find the frequency of a photon, and we're going to get to a photon, what a photon means in the next lecture, but find the frequency of a photon with a wavelength of 434 nanometers. Because our speed of light is given to us in meters per second, when we do these calculations, we need to make sure our units are the same. So we need to convert our nanometers to meters. So how do we do that? Well, we know that 434 nanometers, you can convert it using this conversion. Okay, so our wavelength goes from 434 nanometers to 4.34 times 10 to the minus 7 meters. Our C is the same. And now that we've got this in meters and we have our C, it's easy to solve for our frequency. We just plug everything in at a time. And we get this number, 3 significant figures. That's it. The next lesson we will talk about our light in terms of particles.